Hi, I'm Jeff, and I'm going to discuss some research on listening experiment design for generative systems that I worked on with Philippe. In recent years, there's been a lot of interesting and exciting work involving generative systems. For the most part, in order to benchmark these systems, we rely on listening experiments. However, there are significant discrepancies between studies with respect to experimental design. In this presentation, we discuss recommendations for improvement backed by experimental evidence. We'll start with an overview of experimental design. In the simplest sense, a listening experiment is comprised of three components: participants, questions, and responses. In our context, a question is typically a set of one or more musical examples, which a participant must listen to before providing some sort of response. Depending on the methodology employed, participants may be asked to provide a variety of responses, ranging from predictions on whether a musical example was generated or human composed, to qualitative feedback on various aspects of the musical examples. Of course, to get meaningful results, we must collect more than one response. In this experiment, we have two participants, participant 0 and 1, three questions, questions 0, 1, and 2, and four responses, shown in green. In our study, we are going to investigate the role of two hyperparameters of experimental design: the proportion of experiments, which is simply the total number of participants divided by the total number of responses collected, which in this case is 0.5, and the proportion of questions, which is the total number of questions divided by the total number of responses collected. In this case, it's 0.75. When we design an experiment, we aim to investigate the relationship between multiple factors. There are two types of factors: fixed and random factors. A fixed factor has a fixed number of levels that are of interest to the researcher. One common example in this context is the system factor, as there will be a fixed number of systems being compared in an experiment. The other type of factor is a random factor, where only a random subset of a large number of possible levels, all of which are of interest to the researcher, can be feasibly included in the experiment. For example, participants are a random factor, as there is a large group of possible participants we would be interested in including in our experiment. However, we have to settle for a much smaller subset. In the context of a listening experiment, questions are another random factor, since generative systems can continuously produce new musical samples, but we can only feasibly include a random subset. Once the factors have been established, it is necessary to determine the experiment design, which specifies the relationship between factors. Pairs of factors can be crossed or nested. In a cross design, each participant is exposed to each of the questions, so that every possible combination of participant and question is included in the experiment. As you can see above, participants 0 and 1 are both exposed to questions 0 and 1. When two factors are nested, each level of a factor co-occurs with only one other level. Here, the question factor is nested within the participant factor, so that each participant is exposed to different questions. As a result, only each question is used only once. It is also possible to have a partially crossed design. Here, the participant factor is partially crossed with the question factor, as different participants are occasionally exposed to the same question. You can see that participants 0 and 1 are both exposed to question 0, but question 1 and question 2 are only used once in this experiment. The main difference between these three designs is the proportion of participants. In a nested question design, the proportion of questions is always 1, while partially crossed and fully crossed designs feature a lower proportion of questions. Now that we have a good understanding of what a listening experiment is, and some of the different designs that can be employed, we'll touch on the motivating factors behind this research. First of all, when we make poor choices with regards to experimental design, in the worst case, our results may be completely invalid. At best, these poor choices will reduce the reliability of our experimental results. Secondly, since conducting a listening experiment requires an investment of both time and money, it is in the researcher's best interest to make efficient use of the allocated resources. Finally, and probably most importantly, an overview of recently published listening studies reveals large discrepancies with respect to experimental design. This indicates that there is not yet a consensus on how to design a listening experiment. Here we plot the experimental design of recent studies. It is immediately evident that there is a lot of variance in terms of the number of questions featured in each experiment, shown on the y-axis. In addition, there are a variety of experimental designs employed, including partially crossed, and nested designs, which are notated using triangle, cross, and circle symbols in the plot. This naturally leads to the question, do these variations in experimental design have a significant impact? To answer the question, we conduct two experiments. In the first experiment, we calculate the power for nested question and crossed question designs. In the plots, the contour lines and shade indicate the power of the experiment parameterized by the number of participants and the number of questions per participant. As a result, we can directly compare the power of a nested question and crossed question design, given the same amount of resources. The results demonstrate that nested question designs are uniformly more powerful than crossed question designs. In fact, we found that nested designs were 2.3 times more powerful than cross designs on average. If we take a look at the cross question plot, we see that in some cases there is barely any advantage to adding additional participants. This is mainly due to the fact that adding additional participants only increases the number of participants, not the number of questions, as each participant is exposed to the same set of questions in a cross design. In contrast, with a nested question design, we always see increases in power when a new participant is added. This is because adding a new participant also means the number of questions is being increased, as each participant is exposed to a unique set of questions in a nested design. The difference between these two plots clearly demonstrates that the proportion of questions is important, as cross designs which have a small proportion of questions are uniformly less powerful than nested designs which have a proportion of questions of 1. We can also plot a line which shows how power varies when the proportion of participants is manipulated, while holding the total number of responses and proportion of questions constant. It is evident upon plotting several lines for a different number of responses that in all cases power increases as the proportion of participants is increased. In the second experiment, we calculate the variance of experimental results using different experiment designs. To do this, we start with the raw data collected in an actual listening study. Then we randomly sample a subset of the responses such that our chosen experimental design is satisfied. For example, if we are measuring the variance of a cross design with 4 participants, 2 questions, and 8 responses, we ensure that the subset satisfies these conditions. Then we calculate the average response. This process is then repeated 50,000 times to produce a distribution of average responses corresponding to a particular experiment design. To compare 2 experiment designs, we compute this distribution for each experiment design and then use Levene's test to compare the variance. We repeat this entire procedure 100 times and report the number of times that there was a significant difference in variance. Using the results collected in the Loch Ness listening study, we compared 2 nested question designs, one using a smaller proportion of participants. We found that the experimental design with a larger proportion of participants had significantly less variance in 100% of the trials. Using the results collected in the Bach-Bot listening study, we compared a partially crossed design with a small proportion of questions and a nested question design. We found that the experimental design with a larger proportion of questions, the nested question design, had significantly less variance in 100% of the trials. Using the results collected in Collins' listening study, we compared a cross design with a small proportion of participants with a partially crossed question design. Once again, we found that the experimental design with a larger proportion of participants had significantly less variance, only this time it was in only 95% of the trials. Collectively, the results of both experiments demonstrate that the proportion of questions and the proportion of participants should be maximized, as decreasing either proportion decreases power and increases inter-experiment variance. However, the ideal experimental design must also take other factors into consideration. In particular, we must consider the endpoint of the experiment when designing an experiment. Consider 2 hypothetical experiments. In experiment A, we want to measure the valence of audio clips, and in experiment B, we want to compare system A and B. Note that experiment B is a prototypical example of a listening study. In experiment A, the endpoint of the experiment is an average valence per audio clip. On the other hand, in experiment B, the endpoint of the experiment is not the average rating per clip, as we don't really care how a particular clip is rated. Rather, we care about how a particular system is rated. In both cases, we want to maximize the reliability of our endpoint. In experiment A, this means that we want to maximize the number of questions per audio clip. In experiment B, this means that we want to maximize the number of questions per system. Admittedly, if an endpoint of your experiment is measuring inter-rater agreement, then of course you need to use repeated questions. However, in most cases, this is not the purpose of listening studies that evaluate generative systems. To close, I will offer some recommendations for listening experiment design. Hopefully it goes without saying that increasing the number of responses is always beneficial. However, these recommendations are based on the assumption that resources are finite, as researchers have budgets, both monetary and temporal, that are going to place inherent restrictions on the number of responses that can actually be collected. First, we must ensure that the proportion of questions is as large as possible. So practically, this means avoiding crossed question designs and only using partially crossed designs when they feature a large proportion of questions, and always favoring nested question designs, as those will always have a proportion of questions of one. If we return to the plot of experimental designs we reviewed earlier, we can see that many experiments could be improved by simply increasing the proportion of questions while holding all other factors constant. Furthermore, this is a low-cost fix, as sampling from generative systems is relatively cheap. Our second recommendation is that as much as possible, ensure that the proportion of participants is large. On a whole, researchers seem to be more sensitive to the participant factor, but it's still worth noting that limits should be placed on the number of responses per participant. According to the experimental results, an ideal experimental design would feature one response per participant. However, this is rarely feasible in practice, since there is a cost associated with acquiring each additional participant. All that being said, if you only remember one thing from this presentation, it's that increasing the number of questions, and in other words, the number of generated samples, is a cheap, easy way to improve experimental reliability and power.